This is Mr. Anderson for Keller Community College doing Section 3 of Chapter 7, Multiplying Radical Expressions. And at the start, we'll get our disclaimer out of the way. We will assume that no radicans are formed by raising negative exponents to even powers, so we don't have to deal with plus or minuses or absolute values when taking the square roots of numbers like the square root of 9 is 3, not plus or minus 3. Well, first of all, we're going to start off with looking at the product rule for radicals. And this is a neat little simplification trick. So if we have the nth root of a times the nth root of b, this is going to be equal to the nth root of a times b. As long as they're under the same radical, you can put them together with multiplication. For example, if we have the square root of 3 times the square root of 4. This will give us the square root of 12. And what we're going to learn is how to take this and break this down later on in this section using the product rule. Now, looking at another example here, I do want to bring up a word of caution, and this word of caution is for a popular misconception in abusing the product rule. And this is when you have different roots. So for example, if I have the nth root of a times a different root, like the mth root of b, there's a misconception that we can just put this together and just kind of blend the powers, the n and the mth root and a times b. But this is not the case. You cannot blend two roots of different indexes. If they're different indexes, you cannot do that. So what this means is that if I have the square root of x and the cubic root of y, I cannot put these together. A common mistake is people would put that under the same radical because they say, well, a radical's a radical, right? Well, not if they're of different powers, or different indexes. So that is that. But we can use the product rule to kind of do some pretty cool things. Like, let's take a look at problems 1 through 4 here. In problem 1, we can take these and put them under the same radical as 2 times 3, which is 6. So this is the cubic root of 6. Now here, since they're both square roots, we can take them as x minus y and x plus y and do a little FOIL. And if we did FOIL, we would find that we'd have x squared plus xy minus xy, which would cancel out, or simplified it to 0xy, and then we'd have minus y squared. Now, here's an interesting note of problem 2. We are done with the problem at that part. A common mistake is people will say, oh wow, these both have little squares by them, but since this is a binomial, we cannot just take the square root of this and have this as x minus y, so this is not equal to x minus y. That is, it is an illegal step. It is not part of the problem. You would have to have this whole thing in parentheses with a 2 around it for us to take it out. So legally speaking, if we had x minus y squared under the square root, then we could have x minus y. But this is completely, totally not legal here. Okay, so down here, you'll notice that you might think to yourself, oh boy, do I got to really double distribute this, where I distribute the x here and the negative 1 here if I put them under the 4th root? Well, one thing's kind of nice is that this is factorable to x minus 1, x minus 1. So really I've got 3x minus 1s, so this is the 4th root of x minus 1 quantity cubed. And that's as far as we're going to go there. Here, these are both under the 6th root, so I can kind of combine this to be 5 times x plus 3 and 3 times x minus 2, all under the 6th root, which means in my numerator I'm going to have the 6th root of 15x plus 15, or sorry, 5x plus 15, sorry about that. Hard for me to get rid of that right there, so 5 times x is 5x, 5 times 3 is 15, and then under here I've got 3x minus 6. Okay, so moving on to some simplification using the product rule. And having a root chart is somewhat handy, and let me explain what a root chart is. A root chart is maybe off on the side of your paper. You should try to list some common roots. Like so in the x squared category, common roots would be 1, 4, 9, 16, 25, 36, 49, and so on and so forth by going 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared. X cubed would be 1, it would be 8 and 27, 64, 125, 216, and you won't have to go too far for x to the 4th power because you're not going to see a lot of these come up, and if you do, that would really surprise me. And x to the 5th is just as short because you're just not going to do a lot in these charts right here. Now these charts that I've made for the side here really come in handy when using our product rule to simplify. So let me change colors and talk about the product rule. The product rule, it deals with the fact that we can take any kind of rootable number like AB under the nth root, and we can split that into the nth root of A times the nth root of B, which is nice when we're doing some simplifying. So you'll take a look at problem number 5. Now problem number 5, the square root of 27, you'll notice that 27 isn't in one of these listable numbers here. But do you see one of these numbers in light blue is divisible into 27? It's the 9. So what I'm going to do is I'm going to take that 9 and hold on a second here. Change to a new color. I'm going to take that 27 and divide by the 9. So I'm going to have the 9 times 3. Because according to the product rule here, we can take the two numbers, like 27, and break that into 9 times 3. Now, the square root of 9 is rootable. So this becomes a 3. Now, the square root of 3 is not rootable, so it stays like a 3. And that's really the technique right here. So we're going to look to see what is the biggest number that can divide the number underneath the radical. So take a look at 350 and take a look in which numbers here can divide 350 evenly. And since this is the x squared, we're going to look for these numbers. Now, the number that can divide 350 evenly is 25. So 25 times what is 350? And using your calculator, you can find out it's 14. Then we can take the square root of 25, which is 5, and the square root of 14, which stays the square root of 14. And there's your answer. For a moment, let's investigate some problems, like the square root of 8. The square root of 8 is divisible by 4, and it's also then has to be multiplied by 2 to make that up to 8. So 4 times 2 makes 8, which means we can take the square root of 4, which is 2, and that leaves us with the square root of 2. Let's take a look at another quick example here, the cubic root of 250. And the cubic root of 250 is, 125 times 2, because I looked in my cubic root chart here. And the cubic root of 125 is 5. And the cubic root of 2, well, unfortunately, just stays the cubic root of 2. All right. Now, it gets a little trickier when we have a number like 48. So if we're thinking about 48, what's the biggest number that can divide 48? And I know some of you thought, well, 4 divides 48, but there's a bigger number that divides 48, which is 16. So what this gives us is the square root of 16 times 3. And that square root of 16 times 3 gives us an answer of 4 square roots of 3. Now some of you might have thought, well, what if I divided by 4 in this case? So instead of dividing by 16, I divided by 4, which leaves me with 12. And that gives me 2 square roots of 12. It's just that 2 square roots of 12 isn't the final answer, because the square root of 12 can be broken into the square root of 4 and the square root of 3. So this leaves me with the 4 that can be brought out, so I have 2 times square root of 3, or 4 square roots of 3. It's just that your chances of actually doing the problem right, if you didn't pick the biggest number to remove from the problem, you see, first of all, you can see how much longer it took me to do it. And moreover, I think a lot of people would make a mistake in missing that 12 can still be rootable. When we get to variables, things are a little different here. I'm going to write the steps out and show you that this is the same thing as x to the 6th power times x squared, because you'd add the corners. The 6 and the 2 make a total of 8. So I can write this out again, x to the 6th and x to the 2nd power, all under the 6th roots. Now, as we learned in the previous section, if we have the 6th root of x to the 6th, it leaves us with x, because it's 6 over 6. But that x squared is still not big enough to get out, so this is my final answer here. An alternative to doing this strategy is to ask yourself, how many times does 8 fit into 6? It fits into 6 once with 2 left over. So a quick way to write that is x with 2 left over under the 6th root. So I'll show you both ways how to do that in this problem. But this one, we're going to have to tackle the cubic root. Take a look at this as x cubed up here. So we're going to have to try to find one of those numbers that divides the 32 evenly, and that's going to be 8. So that means I'm going to have the cubic root of 8 times 4, because 8 times 4 is 32. And then now I can take a look at my x to the 6th, so I'm going to write x cubed twice, because if I have x cubed and x cubed, that gives me 3 matches here, so that's going to be x squared. The cubic root of 8 is 2, and that leaves me with the 4 on the inside and the cubic root on the outside. So you got to be careful when you write so this doesn't look like 2x to the 23rd power. This is 2x squared and the cubic root of 4. Now, to slow that down a little bit, I can break these all into separate little radicals. This is the cubic root of 8 times the cubic root of 4 times the cubic root of x cubed times the cubic root of x cubed, because that gives me 3 and 3 to make 6, 8 times 4 to make 32. Now, this cubic root of 8 became the 2. The cubic root of 4 just stayed right there, locked up in the radical. The x cubed and the x cubed became x, and that's how I got my x squared. Alright, we'll be tackling the second video, the next part of this in the next video, so stay tuned and email me if you have any questions.